Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we talk about how we can select a conjugate prior for data with a Poisson likelihood. Let's begin. So, first, let me remind you that the conjugate prior for data with a Poisson likelihood is the gamma distribution family. Okay, so let's talk about the PDF of a gamma random variable first. Let's remember what it looks like. Okay, so we know that our parameter of interest will be mu, the mean for a Poisson likelihood. So let me use mu as our variable. Okay, so g of mu PDF for a Poisson for the PDF for a gamma with parameters r and v, right, will be given by this expression. So it's going to be v to the power r divided by the gamma function evaluated at r times mu to the r minus 1 times e to the negative v times mu. And that formula is valid for positive mu's, perhaps 0. That would be the support, right? Now let me point something out, something that is going to be important. See those parameters, right? R and V. Well, those guys have to satisfy restrictions as well. It turns out that R has to be positive and V has to be positive as well. Okay, that's going to be important to keep in mind. Okay, so that's a PDF, and it's going to be 0 elsewhere, right? For negative mu's, that would be 0. Okay, so something that I would like to mention as well is that you may have seen another expression for the PDF of a gamma. Okay, so maybe you have seen the following PDF instead. So let me use f of y. So maybe what you have seen is something that looks like this. 1 over the gamma function evaluated at alpha times beta to the alpha power times y to the alpha minus 1 times e to the negative y divided by beta. Okay, and the support in this case would be, positive y's. Okay, and we have the same restrictions for alpha and beta, right? What we would need here is alpha positive and beta positive as well. So anyway, it turns out that if you're careful, and you use the second expression, the one we just wrote down, right, you will end up with the same conclusions as you would if you use this PDF. But this is the one that we're going to be using because this is the one that we have in our textbook. And let me just say why the authors from our textbook decided to use this one. Because then you end up with updating rules, right? The rules that allow you to find the parameters for your posterior distribution, right? You end up with easier to remember updating rules using this expression for the gamma prior, okay? And that's the reason, okay? But as I said, you could use either one of these, and if you're careful, if you're consistent, your results will match, okay? Anyway, now something that is going to be useful in this video to select a conjugate prior is remembering what the expected value and the variance for a gamma random variable are. Okay, so very quickly let's derive the formula for the expected value, and then you can derive the one for the variance later on your own as an exercise. So let's find the expected value of a gamma random variable. So if mu has a gamma distribution, so let me say that this guy has a gamma distribution, so we know that the expected value of mu would be the integral from 0 to infinity, because you know, the other part, it would be from negative infinity to infinity, but we know that it would be 0 for negative mu's, so we end up with only this, right? So let me just write down the one that is going to be important, different from 0. So it would be the integral from 0 to infinity, in this case, of mu times the PDF, which happens to be this guy. And we are going to be integrating with respect to mu. So now, let me pull out that constant that doesn't depend on mu, so it is not going to be important to have it inside that integral. So we pull it out, right? And then mu times mu to the r minus 1 is the same as mu plus r minus 1. Agreed? So let me change that exponent, right? Okay. So now, as you can see, the integrand, this quantity inside our integral, looks rather similar to the kernel of another gamma random variable. But this one here has parameters instead of r plus 1 and v, right? So we have done this before, so let's complete that gamma. So now this guy would be r plus 1, r plus 1, and now this inside that integral is the PDF of a legit probability distribution, a gamma random variable with parameters r plus 1 and v, right? But we multiplied by this guy. So let's divide by that guy, okay? So let me place this one here, since we divided by gamma evaluated at r plus 1, let me place it here in the numerator, and since we multiplied by this guy, let's divide by that guy outside that integral, and then we are just multiplying by a1. That's something legal from a mathematical point of view, but then we know that the purpose is completing that gamma inside the integral, and since we are integrating over the entire support, the region where the PDF is different from 0, then this is going to be a beautiful one. Okay, so now what we have is this. If r was an integer, it doesn't have to be, but if it was an integer, we know that gamma evaluated at r plus 1 is going to be just r factorial, right? Okay, but in order to simplify this, we are going to use another property that we should remember from sta360. So let me just write that down, and then you can check that later from your notes, you know, from sta360. And the proof is easy. Just use the definition of the gamma function and integrate by parts. That's a proof. Okay, so from that we have that gamma evaluated at r plus 1 is the same as r times the gamma function evaluated at r. Okay, that's a property of the gamma function. Okay, so let's use that property to simplify this. So first we have v to the r power divided by v to the r plus 1 power. Then we end up with only a v in the denominator. Agreed? And then since we have gamma to the gamma evaluated at r plus 1, what we have here is r times gamma evaluated at r divided by gamma function evaluated at r okay, there we are, right? So that v, right, v to the r divided by b to the r plus 1, we only have this guy here, right? And then gamma evaluated at r plus 1 is the same as r times the gamma function evaluated at r, right? So these guys cancel out, and in the end what we have is the expected value is r divided by v for a gamma with parameters r and v. Agreed? Okay. Okay, now then later, right, homework, you can check that the variance, if mu has a gamma distribution, the variance will be r divided by v squared. Okay? Okay. And it's going to be similar. Proof is going to be similar. Okay, so now that we have the expected value of our gamma random variable and our variance of our gamma random variable, we are ready to move on. We can talk about our strategy to find r and v, the parameters of our gamma prior. Okay? So the idea will be the following. Let m be your prior mean. Okay, prior mean. You have a particular value for the mean in mind, one that reflects your initial beliefs about that parameter mu that we are interested in doing statistical inference, right? Okay. And then you also have, let me call that guy S, your prior standard deviation. Okay? So the strategy that we're going to use to find our gamma prior is this. We are going to find the numbers R and V that match those two prior quantities, the mean and the standard deviation. Okay, so basically it's going to be just solving the following system of linear equations, right? So find, that's going to be our strategy, find R and V such that M, your prior mean, equals R divided by V, because we know that that's the mean, the expected value for a gamma random variable. So that's going to be your first equation, if you will. And then the other one will be, we're going to square your prior standard deviation, and we're going to match that with this, the formula for the variance of a gamma random variable. Okay, that's your second equation. Make sense? Okay, so there are a couple of different ways that I can think of to solve that system of linear equations. Well, not linear, that system of equations, right? So one way of finding these guys, one way. So from here, right, from the first equation, what we could do is we could solve for R, right? And if we solve for R, we will have that R equals M times V. Make sense? Okay, so R equals M times V. That will be our new equation. Let me call it let me call it I. Okay? Or 1 prime. I don't know. Okay, yeah, 1 prime. Now, let's do the same for the second equation. Okay, let's solve for R. Okay, so if we do that, then from here, what we will have is this. R will be the same as S squared times V squared. Make sense? So S squared times V squared. And that would be 2 prime. Okay, so now we just since by 1 prime R equals M times V, and by 2 prime R equals S squared times V squared, well, that implies that MV must be equal to SV squared, right? So from 1 prime and 2 prime. M times V equals S squared times V squared. Okay? Which also implies that we have the following quadratic equation. We have S squared times V squared minus MV equals 0. Make sense? I'm just placing this guy here, right? I'm subtracting MV on both sides, and then SV squared minus MV must be equal to 0, right? Now, let's factor out 1V, okay? So what we have here is V times S squared, that's our first term, times V, right? We need another V, minus M, right? We want that to be equal to 0. Okay? So one option would be, hey, how about V equal to 0? And then we go to the restrictions of a gamma PDF, and we go, oh, V and R must be greater than 0. So yeah, V equals 0 is a solution for that equation, but that doesn't work for us, right? So one solution, V equals 0, right? But that is not going to be helpful for us, right? V equals 0 doesn't work for us. The other one would be if this guy here, that second term, right? If V is 0, then 0 times this, that's 0. Okay, but that doesn't work. The other option is, how about this guy is 0, right? This guy is 0, right? Then that implies that M must be equal to SV squared, right? And remember that what we're trying to do is we're trying to find the R and V that work for us, right? So what we have here is that S squared times V equals M, which implies that V is going to be M divided by S squared. Make sense? V equals M divided by S squared. Okay? And then, if that is the case, right, we know that R is the same as this or this. Let's use 1 prime. Okay? Or let me see. Oh, guess what? Let me use this one here to prime, because since I'm going to be multiplying by S squared, then this guy will cancel out. So let's just say that. So we have already solved for V. Let's find the R that is going to define our gamma prior. So as we were saying, by 2 prime, what we have is that R equals S squared times V squared which will be the same as s squared times, oh, no, then the one I want, let me change my mind and do this with yeah, no, that's fine. Okay, either way works. So let me just do this one here. It's the same, either one will work. So it would be this one squared. So then what we're going to have is m squared, right? M squared, and then divided by s squared, right? Because we have s squared squared, right? So one of those will cancel out, and that's what we end up with. So bottom line, right, the parameters r and v that will define our gamma prior will be given by the prior mean divided by the prior variance that defines our v, and for r is going to be m squared, meaning the squared of our prior mean divided by our prior variance. Make sense? Okay. One more thing, precautions slash suggestions. Precautions slash suggestions. So one, graph your prior, okay? So graph your prior. So the shape of your gamma with parameters r and v should match your prior beliefs about it, okay? It must be centered around you know, the value that you think is or values that you think are more likely, and the spread that you see there, you know, should match with the idea about the variability with respect to that value or values, okay? The other one, it would be a good idea to calculate something called the equivalent sample size of your prior. We talked about this when we discussed data with binomial likelihood, okay? So calculate the equivalent sample size of your prior. So there are two ways to find the equivalent sample size, okay? Let me show you both ways, and as long as you remember one of them, that's fine, okay? So just remember that you could translate the information that you think you have, your prior information, in terms of a number of observations, right? There's an equivalency there, okay? Back then, when we talked about binomial likelihoods, it was in terms of as if you had seen previously a prior sample with a number of successes and a number of failures, right? In this case, it's going to be the same idea, but it's going to be slightly different, right? Your equivalent sample size will be in terms of, you know, the parameters of gamma prior, right? R and V. Okay, so first, one way of finding that equivalent sample size of your prior. So note that if you have, you know, observations, let me call them Y's, from a poisson with parameter mu, then the expected value is mu, right? No problem, we know that. Mu. And a nice feature of Poisson is that the variance of a Poisson is the same as its mean. Okay? Mu as well. So now let's find the expected value of y bar, the sample mean. So the expected value of y bar would be the same as the expected value of y1 plus y2 plus y3 plus ... yn divided by n. Agreed? So let me do that. y1 y2 ... yn divided by n. We know that the expected value is linear, right? So we can factor out that constant. So 1 over n, and then we have the expected value of that beautiful sum of random variables. We know again that the expected value is linear. In this case, what we mean by that is that the expected value of a sum is the sum of expected values. So we would have expected value of y plus expected value of y2 plus expected value of yn. So what we end up with is n times the expected value of those guys, right? So what we end up is n times mu divided by n. So in the end, this happens to be just mu. So the expected value of y bar is equal to mu. Okay, for those who are taking sta360, this would be the proof that y bar, the sample mean, is an unbiased estimator for the mean, the true mean mu. Okay, anyway, so now let's do something similar for the variance. So for the variance, we have variance of y bar, variance of y bar, but then what we have to do is when we try and pull out that constant 1 over n, we have to be careful. Now we have to square that constant, so it's going to be 1 over n squared. Squared of 1 is 1, and then we just square this one here. Okay, and then we have the variance of a sum. Now these guys, y1, y2 up to yn, will be independent. We will have independence between our observations, and that will be very useful because then the variance of a sum of independent random variables is the sum of variances, right? We know that from sta360. So what we end up with here is with n times the variance divided by n squared, right? So n times the variance, but the variance for a Poisson happens to be mu. So we end up with n times mu again divided by n squared. So in the end, what we have is that the variance of y bar is mu divided by n, right? Once we simplify that expression. There we are. So, now, why would this be useful? Well, you have the variance of y bar, okay? So, it turns out, right, that the equivalent sample size, if you take a look at the variance of y bar, right, is mu divided by n. And well, and we're going to see that in a sec in terms of the likelihood. You know that the variance of a gamma random variable is r divided by v squared, right? So if you equate this with that m divided by n, and you solve for n, that guy is your equivalent sample size, okay? So the equivalent sample size will be the solution of this. And let me emphasize that this guy here is that n is the equivalent sample size, okay? And we want the solution in terms of the variance for our gamma prior, right? Here we have it. Where do we have it? Oh, there. Okay. So let's solve for n. So what we have is just we multiply by this guy and then we divide by that guy. So what we end up with here is this guy happens to be mu v squared divided by r, mu v squared divided by r happens to be equivalent sample size. And if we set mu equal to r divided by v, which would be the prior mean, right? Okay, no problem. So setting mu equal to r divided by v, r divided by v, which is the prior mean for gamma. What we end up with is this, right? So we have mu would be r divided by v, times v squared divided by r, v squared divided by r. Okay, we're almost there. Yeah, I know, we're almost there. So that's going to be your equivalent sample size. Make sense? These guys will cancel out and we will end up with the following. Okay? Give me just a sec. So it's going to be V equals N, right? The equivalent sample size will be just V. Make sense? Can you see that from this, right? These guys will cancel out. We only have a V, right? V equals the equivalent sample size. Let me write that down in another file here. So our equivalent sample size will be V. Make sense? And that's from what we had here, right? These cancel out. We have V squared divided by V. That's our equivalent sample size. Okay. Equivalent sample size. Now, let me just, to wrap this up, give you a justification as to why we equate the variance of y bar, right, to the variance of our prior distribution. Okay, so note the following. Note, we know that the main ingredients in Bayesian statistics is the likelihood and the prior distribution, right? Okay, so let me write down the likelihood for a sample of y1, y2 up to yn. Okay, so here we go. Likelihood. Okay, so it would be the probability of observing particular values y1, y2 up to yn. That's our sample, right? Of observing those guys given the value of our parameter mu. Okay, we know that if you want the likelihood of a sample is going to be the product of the individual likelihoods, right? And the likelihood of a single observation is given in this case by evaluating the probability mass function for each of these guys. Okay, so it would be mu to the power y1 for the first observation divided by y1 factorial times e to the negative mu. Okay, so I am using the proportionality symbol in order to save some time, right, and some effort, and then I won't be writing that y1 factorial here, right? And it is a constant with respect to our parameter of interest mu. Okay, anyway, so that's why I'm using the proportionality symbol here. So we have mu here, and that's just the likelihood for the first observation times the likelihood for the second one, and so on, right? We have n of these observations. So dot, and then we have the nth observation, once we do the algebra, that likelihood for that sample is equivalent to this: mu to the sum of yi's, okay, y1 plus y2 plus y3, and so on up to n, right? Dot dot dot. And we have e to the power n times mu, right? Agreed? That's the likelihood, okay? Now let's talk about the other important ingredient, the prior distribution, okay? Prior. So the prior is just the probability distribution of mu, of our parameter of interest, right? We regard that guy in Bayesian statistics as a random variable. And this guy, we said, is going to have a gamma distribution. We will be using a gamma prior, right? Let me just remind you that gamma with parameters r and v, right? That's what we're using, a conjugate prior. And if we think about the kernel, right, meaning the PDF, but ignoring the constant that makes it a legit PDF, right, that makes it integrate to 1, then what we have is mu to the power r minus 1 and e to the power minus v times mu. So if you compare these two expressions, right, now what we did before with the math that we did before, right, remember that our conclusion was that the equivalent sample size was v, right? So then if you compare these two, you go, oh right, v and n. If I'm using this as a prior, is if I had observed, you know, a sample of size, you know, well, a sample of size v. Make sense? Got it? Okay, so let's summarize what we did here together in this video. So what we wanted to do was solving the problem of selecting the parameters r and v for our conjugate prior for a Poisson likelihood. Okay, so what we said is what we're going to be doing is we are going to come up with these two values, a prior mean and a prior standard deviation, that reflect our initial beliefs about our parameter mu, right? Then we use the expressions for the expected value of a gamma with parameters r and v, and the variance for a gamma with parameters r and v, right? And we set up a system of equations. We solve for r and v, and there we are. We have the parameters of our gamma prior, right? But then once we have them, we said it would be a good idea, number one, to graph your prior to see that it makes sense to you, okay? And the second point that we need to check is if, you know, your equivalent sample size matches with the kind of prior information that you believe you have about your parameter mu, okay? And what we did is we realized that the equivalent sample size happens to be equal to the parameter v. Okay? And we justify that, right, using first just comparing the expressions of the likelihood and your prior here. And what we did here was a little bit of algebra, and we used a little bit of probability theory. Okay, and we just end up with the same conclusion, that the equivalent sample size in this case would be the parameter v. Okay, makes sense? Okay, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.